So in today's video, we're going to go ahead and actually start delving into these different methods of integration. And the first technique we're going to learn is the reverse power rule. And so as we're going to come to find, a lot of integration is essentially just reversing what we learned in differentiation. And that's directly the case with the reverse power rule. And so the reverse power rule essentially applies to different polynomial functions, and it tells us that if we want to take the integral of x to the n dx, right? So x to the n, where n is just some real number, except n can't be equal to -1. We'll see why a little bit later on. Then this is just going to be given by x to the n plus 1 divided by n plus 1, and then of course we can't forget the plus c over there. And so if you want to look back at, our differential calculus playlist and the power rule itself in differential calculus, it tells us that if we wanted to take the derivative with respect to x of x to the n, then that's just going to be nx to the n minus 1, right? So we decrement the exponent and then we multiply by the original exponent, right? We multiply by the original power. And so when we're taking the reverse power rule, we do pretty much the exact opposite of that. We increment the exponent and then we divide by that new incremented exponent. And so if you want to see why this actually works, you can go ahead and differentiate both sides. So the derivative with respect to x of the integral of x to the n dx, that's going to be equal to the derivative with respect to x of x to the n plus 1 over n plus 1 and then plus c. So you can kind of think of these two canceling out. Again, not very rigorous, but it does give a general sense. And then over here, the derivative with respect to x plus c is going to disappear, right? Because the c is just a constant. And then the derivative with respect to x of x to the n plus 1 over n plus 1. That's going to be equal to, again, n plus 1. We're going to decrement the exponent, so minus 1. And then we have n plus 1 in the denominator, and we're going to multiply by n plus 1, right? And so these are going to cancel out. The plus 1 and the minus 1 are going to cancel out, and we'll just be left with x to the n. And we know over here that since the derivative and the integral kind of canceled out, then we just get x to the n equals x to the n. So you can kind of see why this actually works. We're essentially doing the exact opposite of the power rule in differentiation. And so let's go ahead and do a couple of examples of this to make it a little bit more concrete. And so here we have the indefinite integral of 2x dx. And so from our integral properties, we can take the 2 out if we would like, and then we'd just be left with the integral of x dx, which is just going to be 2 times, again, this is kind of just x to the 1, right? And so if we wanted to apply the inverse power rule, we would increment the exponent and then divide by that new incremented exponent. And then this is going to be equal to 2 to the x squared over 2, right? And then these 2's will cancel out and we'll just be left with x squared. And then we can't forget to add that plus c at the end. And so when we're applying the reverse power rule, we don't necessarily have to worry about the plus c until the very end, because you kind of think of any scaling factors like this 2 over here. This scaling factor won't really impact that plus c because it'll kind of just be absorbed into the constant, because when we multiply two constants together, we just end up with another constant, so it doesn't really matter. And then with respect to this polynomial function over here, again, we know that when we're integrating the sum or difference of different functions, then we can just integrate each individual term. And so this is exactly an example of that. So let's go ahead and do that. So right over here, the integral of x cubed, we're going to just go ahead and take, we're going to increment the exponent, so x to the 4th, right, because 3 plus 1, and then we're going to divide by that new exponent. And then same thing with 8x, right? 8x, we're going to increment the exponent, because here we have, the power of 1. So we're going to increment it, so we'll end up with 8x squared, and then we're going to divide by that new exponent, so we'll get 8 over 2x squared. But 8 over 2 is just 4, so we can go ahead and simplify that. And so this will just become 4x squared. And then finally, 7. So 7 can be rewritten as 7 times x to the 0th power, right? And so when we actually increment the exponent, we'll just end up with 7, okay, what's happening? 7 times x to the 0 plus 1, which is just x to the 1. And then we're going to divide that by 1, but we know that 7 over 1 is kind of just 7. So we're just going to end up with plus 7x. And I encourage you to actually take the derivative of this expression, and of course we can't forget the plus c. Take the derivative of this expression, and you will notice that we will actually end up with this exact expression, this integrand right over here. And even up here, the integral of 2x, we know that 2x is the derivative of x squared, but we have to add this plus c over here because when we take the derivative, this plus c is a constant, so we'll just disappear and we'll only be left with 2x. So that's I hope that kind of clarifies why we do need this constant of integration. And then finally here we actually have a definite integral now, the integral of 3x squared plus 2 dx. And the way that we would approach this is we would just find the antiderivative and then evaluate it at the two endpoints. And so let's go ahead and actually do that. So 3x squared, we can kind of just go ahead and we can first of all look at it by observation and think that the derivative of x cubed is just 3x squared. But if you wanted to apply the power rule, you could go ahead and do that, or the reverse power rule, you can go ahead and do that and you would end up with the same result. So x cubed over here. And then plus 2, again, this is a 2x to the 0, and we know that 2 is just the derivative of 2x, so this is just going to be plus 2x. And then you could add the plus c over here, but I mean, when you're doing definite integration, it doesn't really matter to add the plus c, because when you do evaluate at the two endpoints and then subtract them, then the plus c is going to cancel out. I mean, I can illustrate that for you if you'd like. So we can add the plus c here. And then we're just going to evaluate it at the two endpoints, so at 3 and 1. And so when this is evaluated at 3, it's going to be, what, 27 plus 6 plus c. 27 plus 6 is just 33. And then if you recall from our second fundamental theorem of calculus, we're just going to subtract it from it being evaluated at the second bound point of integration. And so that's going to be 1 plus 2 plus c, right? So that's just going to be 3 plus c. And then if we go ahead and just kind of distribute, there's going to be 33 plus c minus 3 minus c. And so these two c's are going to cancel out, and then we'll just end up with 30 as our definite integral value. And this is always going to hold true whenever you have a definite integral. So you never really need to add that plus c when you're doing definite integration, or at least for the reverse power rule, because it will cancel out, it will disappear. So you really just care about finding this portion over here. You don't really care about the constant of integration. But when you're doing indefinite integrals, you definitely should include the constant of integration, because otherwise you aren't really getting the most general form of the antiderivative. So I hope this kind of clarifies different things. In the next video, we're going to look at how we can extend this to fractional and negative exponents as well.